Another way we can think about the relationship between these two frames, frame A and frame B, is that they are related by a single rotation about some arbitrary axis in space. So the challenge becomes then to determine what is this axis of rotation. It's a vector we're going to define as v, and what's the amount of rotation around that vector, which I'm going to call theta. So the problem is to discover what is v and what is theta that allows us to rotate frame A into frame B. In order to find the axis around which we rotate, there is a key observation, and that is that the axis around which we are going to rotate must be unchanged by the rotation. Any point that lies on the rotation axis will be unchanged by rotation. And that implies that the rotation axis must be an eigenvector of the matrix R. A rotation matrix has got three eigenvectors. There is one eigenvector which is guaranteed to have elements that are real numbers, and it corresponds to the eigenvalue of 1. There are two complex eigenvectors, and they correspond to complex eigenvalues, which are functions of the rotation angle theta. To illustrate this, I'm going to create a rotation matrix. It doesn't particularly matter what the value is. I'm going to create it using Euler angles. 0.1, 0.2, 0.3. And there it is. And I can see what that orientation looks like by plotting it. There we see the rotated coordinate frame corresponding to this rotation matrix. Now I'm going to look at the eigenvalues of this rotation matrix. And we see that there are three eigenvalues. We'd expect that. It's a 3 by 3 matrix. And the last eigenvalue is equal to 1. I can look at the eigenvectors as well by asking for two output arguments from the eig function. And now we see in the matrix V, each column of matrix V is an eigenvector. And we're interested in the third eigenvector because the third eigenvalue was equal to 1. And we can see that this third eigenvector is real. The imaginary part of all the elements are equal to 0. In order to find the amount of rotation as well as the axis of rotation, we would use the toolbox function tr to angle vector and pass in the rotation matrix we're interested in, and it tells us that we need a rotation of 0.44 radians around this particular vector. Now I can get it to put those into variables by providing two output arguments, tr to ang vec, and the output variable theta has been set to 0.4466, and the output variable v has been set to the vector around which that rotation would occur. So the problem comes down to finding the eigenvalues and eigenvectors of the matrix R. The eigenvector corresponding to the eigenvalue of 1 is our rotation axis v, and from the complex eigenvectors, which are a function of theta, we can determine the rotation angle that we require. Now let's consider we want to do the inverse, that we have the rotation angle theta and we have the vector about which we rotate called v, and we want to find the rotation matrix. Then the equation we need is what's called the Rodriguez equation, and it relates r to v and theta. The inverse operation is performed by the function angvec to r, converts an angle and vector representation to a rotation matrix. I pass in the rotation amount and I pass in the vector, and here is the rotation matrix, and it's exactly the same as the rotation matrix that I started with. You'll notice that the matrix in here is a skew symmetric matrix, and this is a type of matrix that we've encountered already and we'll encounter a few other times in this course of lectures.